here. Okay, for the washer method, the same idea of using the slicing technique. This time you have like the area of, area of the region bounded by the two curves, okay? And the axis of revolution is not part of the graph, or is not part of the one side of the graph. So like for this situation, just for this example, you have the area R, the region R, sorry, and then the axis of revolution. You see you have the empty space between, or the region is above the axis of revolution. When you rotate, the solid object will have the space in the middle of the object, in the middle of the piece. So the empty part here, the space here, if you cut or you slice it, slice means you do perpendicular to the axis of revolution again. When you take one slice out, the empty part or the space in between, in the middle of the solid object here, for the washer or one piece, if you take it out, you're gonna have like the washer. That means you have the circle, the bigger one and the smaller one. We call the outer circle and the inner circle. So to find the area of the washer, you're gonna find the area of the two circles and subtract them. Okay, what we do, since the outside here, I use the R subscript out as the outer radius. And then the R in as the inner radius. So the area of the washer gonna be the area of the bigger circle subtracted by the area of the smaller circle. So the bigger circle will be pi times the R out, or the outer radius squared, minus the pi times the R in, or inner radius squared. Both of them have the common factor pi, so you can factor the pi out and then just work on the square of the outer radius subtracted by the square of the inner radius. Okay, outer or inner, so the graph will help you determine which one which, okay? So that's the concept. So let's see the first problem. And I'll walk you through slowly for each one of them. Like this problem, as a region bounded by the curves, use the washer method to find the volume of solid generated when R is revolved about the given axis. Given the x-axis as the axis of revolution, the function, as you see, it looks very basic, right? The parabola, the y equals 1, and the x-axis. The same as what we did last time. But again, we're gonna look at just the first quadrant, so quadrant 1. So what we have, the figure, the parabola, the y equals 1, and the x equals 0. The region bounded by these three graphs. About the x-axis, we're gonna rotate about the x-axis here. So this is the axis of revolution. For the washer is still part of the slicing technique. So you're gonna do the cross section perpendicular to the axis of revolution. When you do the cross section, so that is the x position, and the x will be from the lower limit 0 to the upper limit 1 as the intersection point here, which is 1, 1. Okay. With this setup, you know the thickness of the washer, which is delta x or the dx. Following part, the interval of integration, x will be from 0 to 1. The next part, you're gonna find the outer radius and the inner radius. I put the R, let me clean up here. So gonna be the R out or the outer radius, whatever it is, the inner radius, and what we're gonna determine in a minute here. So for the when you rotate it, the figure will become something like this is original one, rotated. So gonna form the solid that looks similar to this. And after that, we do the cross section. The cross section, each cross section portion will form the washer. And the middle part is empty. That's the empty part around the axis of revolution. Okay. Now, the outer radius will be measured from the highest part of the point to the axis of revolution. Okay. So that's the R out. So R out, the top part, this is the line y equals 1. So it's going to be 1 minus the y-axis. The x-axis is 1 equals 0. So 1 minus 0 or just 1. So the outer radius is 1. The inner radius gonna be the part that the part that you don't include into the solid object. So based on this cross section, I'm gonna clean up real quick here. Should we do another one? Okay, that's my cross section. So for the inner radius, wow, where did it go? The inner radius gonna be the lowest part of the graph to the axis of revolution. And the lowest part based on the graph y equals x squared. It's gonna be x squared. This is the R inner, okay? Gonna be the x squared minus 0. So x squared minus 0. We have outer radius, inner radius. The next part, you put them all together as a volume. Volume equals the integral from 0 to 1, lower limit, upper limit here. The gonna be pi multiplied by the outer radius squared minus pi times the inner radius or the R in squared, and then multiply by the thickness. You see the setup always the same concept, but the function depends on what you are provided in the problem. All the pieces together, since both have the common pi, we take the pi out, then integral 0 to 1. The outer radius is 1, so 1 squared, minus the inner radius, which is x squared, but we squared. The thickness is dx. Okay, the setup is almost done. So I'm gonna put in the cleaner one. So the same information here, but we see the cleaner graph and cleaner solid up revolution. So far we have the volume set up as pi multiplied by integral from 0 to 1. The outer radius 1 and square to be 1 minus x square gonna be x to the 4th. And the thickness is dx. So the setup is done. The next part, you find the antiderivative. Antiderivative of the 1 with respect to x, you get x. Antiderivative x to the 4th, x to the 5th over 5. Evaluate from lower limit to upper limit. Upper limit first, subtracted by lower limit. And the answer comes out to be 4 pi over 5.